Do we have any questions? Yeah, go ahead, Parker.
For number 3, for number 2.
On the
On the
signature assignment?
Yeah.
Okay.
I was having trouble finding out
What the state of matter is?
Yeah, the state of matter.
Okay.
Especially like the reactants.
Yeah. Okay. So, let me pull it up here. All right, it says we have carbon dioxide with lithium hydroxide, right? Okay, so you got lithium hydroxide, and I hope we know that's what it is, right? Because lithium is 1 plus, hydroxide is 1 minus, you cross them, it's a 1-to-1 ratio. And it says, do you know what this is?
Like the product.
The state of matter.
Oh.
What?
Solid.
Why solid? What makes you think it's a solid? I'm not saying you're wrong. I just want to know why.
It's because it's a pellet.
Yeah, it's a pellet,
Yeah,
right?
solid.
Pellets are solid, right? It's like a salt pellet, right?
Could it also be because like it's like an ionic bond like that? Could that also be why you make it a solid?
It's mixed
Like a
with
salt.
gas.
Like
I mean, it could be an aqueous solution, right?
it could be like a salt, I meant like potential lithium.
Yeah, it is a solid. Now, generally, salts are solid. They're crystalline solids when they're by themselves. But if you throw it in water, it becomes aqueous, right? So you could have recognized that this is an ionic compound, so it's a solid. Perfect. Okay, with carbon dioxide as a gas. All right, and it says that it makes what?
Lithium carbonate.
Lithium carbonate. What's the chemical formula for lithium carbonate?
Li2CO3.
Li2CO3. Does anybody have a question on how we know that's what it is? No?
It's like a displacement reaction, something.
Double replacement reaction?
Displacement.
Not displacement. Well, double displacement, sometimes it's called that. Not exactly, but what else does it come?
Water.
Water, it tells us. And water, does it say water or does it say H2O?
Water.
It says water in the holding tank? Okay, and we know water is a liquid, right? Okay, so the only question is lithium carbonate. What is that?
Solid.
Is it a solid?
Yeah.
Could be. If the water goes away and just goes in the holding tank like it said, yeah, we could just say this is a solid. But if it was together in water, we would call it what? Aqueous. Because this is soluble in water because it has an alkaline metal in it, right? So I'm okay either way. I mean, seeing there's water with it, my mind says it must be aqueous. But if somehow the water gets in the tank by itself, then I guess it is a solid, right? So, yeah, I'll take it either way. Did that answer your question?
Yeah.
Anything else? Then don't forget to balance that equation, right? If you don't balance it, all the remainder of this assignment is going to be wrong-ish. This is a review period, question period, I have no new information for you. So I hope you've come with questions. Yeah, go ahead, Parker.
I have another. So for number 3,
Uh-huh.
I got the balanced equation.
So what is the balance equation?
2LiOH
Okay,
plus CO2. Yeah, that's all.
that's it?
Yeah.
All right.
But I didn't know how much carbon dioxide to begin with.
Did you do number 1?
Yeah. Oh, take that. Oh, okay.
So how much did you get for number 1?
I got 12.
12 kilograms. Okay, yeah. So that's how much we need to get rid of, right? So did you guys read the whole problem here, Houston? We have a problem. Did y'all read that?
Yeah.
You guys ever see Apollo 13 movie? Old movie with Tom Hanks in it. So it's kind of that's a true story. This isn't necessarily a true story. This is just kind of a chemistry twist on it, right? But in that movie, then there's a problem, and the engineers on Earth have to help the astronauts make something that's not made. They have to invent something that will help them stay alive. Okay, and so that's kind of what we're doing here. We're going to help them stay alive. There's 3 astronauts on there, and they're going to be breathing out, and they're trying to conserve their oxygen intake so that they don't produce a lot of carbon dioxide. And this carbon dioxide is just going to suffocate them. So they need to react it and get fresh air in there, right? So that's the whole point. And so, we need to get rid of 12 kilograms of carbon dioxide. And this packet kind of goes through to help us to react with those 12 kilograms of carbon dioxide and help them to live. Anything else?
So in number 3, we are only looking for the how much lithium hydroxide.
Lithium hydroxide, yes, says
Like how
calculate the quantity of lithium hydroxide is required.
How much we need to set it out at 12 kg per.
That's right. To react with all the carbon dioxide that we have.
That's it. We are looking for.
That's it. So we're just using stoichiometry, converting. Yeah, right. That's it. No, not too bad, is it? When you first look at it, some of these look kind of, but it really isn't that bad. Go ahead.
For number 3, do you have to find the limiting reagent, or is that
So we already found out how much carbon dioxide we need to react, right? So that means we need to match how much of the other reactant to completely react with all 12 kilograms of carbon dioxide. So in this case, the limiting reagent is carbon dioxide, because we have to get rid of that. We have to use all of that, right? We have to react all of that so that it goes away and we don't breathe in carbon dioxide. Good? But good question. Anything else? Should we just talk a little bit about each one of these? Or do you have questions?
Like in number 4, we are going for the 80% efficiency.
Uh-huh.
We are just dividing the answer of number 3 with the 80%. Is that it?
So we don't want to just do 80% of it, but let's think about what's going on. If our system that we have to react with this carbon dioxide and lithium hydroxide is only 80% efficient, that means whatever we put in, whatever amount of lithium hydroxide we put in, it's only going to be 80% efficient. So if we find an answer on number 3, what do we get on number 3?
30%.
13.09 kilograms of lithium hydroxide. If we react all of that 13.09 kilograms, our system is only 80% efficient, so that means all of it won't react with all of the carbon dioxide. So that means we need more, right? We need 20% more, right?
Yeah.
Does that make sense? It's just a percentage.
Can we just divide the answer with 80%? That will be with the rest of the.
Will that be correct?
Yeah, it's like
Okay.
16.36.
15 or 16?
16.36.
That sounds pretty close.
It's closer.
Oh. Yeah, it's really not a hard. Yeah, it's just so let's think about this. So if our system is only 80% efficient, and let's say we have 13.09 kilograms, that's the number you got, right, of lithium hydroxide. If we react all of this, then it'll react all of the 12 kilograms of carbon dioxide, right? But this is only 80% of what we need. Do you see how I wrote that kind of as a word equation? And we can change this to a mathematical equation. We have 13.09 equals, right, is 80% of, what is of? Multiply, right? But 80% is 0.8, right, of x. So how do we solve for how much we actually need? Divide by 0.8, yeah. That's it. Is that what you did?
Yeah, just divided by 80%.
Yeah.
That's the same thing.
Uh-huh. Does that make sense to everybody? So we actually need more than 13.09 kilograms, if that's right. I don't know if it is correct, but no, it sounds good. All right. If I remember right. Anything else? Should we look at number 5? Or do you have other questions? And we also, this could also be a questions for Unit 4 test. You guys going to take Unit 4 test this weekend? Good. Because if you wait too long, we got a final test that's in class, right? I would for sure take the unit test before you take the final test. Hopefully you've already taken the practice test. If you haven't, well, do that before you take the unit test, Unit 4 test. Okay, number 5 says, calculate how many cartridges of lithium hydroxide we need. It tells you a little bit of information. 3 pounds of, so each cartridge contains 3 pounds of lithium hydroxide. 1 pound is equivalent to 0.45 kilograms. That's just a conversion factor, right? And we also have keeping the efficiency. We are only 80% efficient. So we want to know how many cartridges of lithium hydroxide we need. And it kind of baby steps you through. Part A, calculate the number of kilograms of lithium hydroxide present in each cartridge, in one cartridge, right? So what's that used for? Why do we need to do that? We're just finding another conversion factor. That's it. So we can convert our 13.09 kilograms into cartridges, right? That's it. It's the only purpose of Part A. Part B, use the efficiency, determine how much extra lithium hydroxide you need. Well, we need to react 13.09. According to Vir, we need 16.3 something, right? So how much excess lithium hydroxide are we going to need? Well, you guys can figure that out. Okay. And then convert from lithium hydroxide into kilograms of carbon dioxide and compare it with number 1. We're just going backwards, guys. We're just double checking. Why do we do this? Why are we doing this? If we're trying to protect people up in outer space, help them come home safely, we better double check and triple check what we're doing. We better not give them wrong information, right? So that's the whole point of this. Then number 6 says we'll need to add 1 more just to make sure we got it right. And it'll kind of make sense why we do that, I hope. Because if you need 10.5 cartridges, what should you do? Round it up to 16 or 11, whatever it was, right? Okay. Just so that you for sure have enough. That's it. Okay. And then number 7 is calculate how much water is produced. It's the same process of number 3 and number 1, right? Does everybody understand this? And then number 8.
Yeah, how to draw the three-dimensional representation?
Okay, here we go. Three-dimensional. Well, if it looks lithium carbonate, it's Li2CO3, right? Well, if we draw carbonate is something like this, right? Double bond somewhere. And then you got lithium hanging out over here. You actually got 2 of them.
So do we need to put some negative signs on the oxygen? Two of the oxygen.
So, yeah, these are partial negative, right? Yeah.
That's all.
And so it might attract over to here, right? And if you're not sure if you're doing it right, I have a good friend that can help you out. His name is Google. Right? I mean, this one is kind of a tough one. But some of the others you should be able to get, like water, right? Because are you doing lithium carbonate here? Yeah, okay. Anything else on number 8? So, yeah, you asked. Did you get my message back? Okay.
Yeah, exactly.
Okay. Yeah, you can use pen or pencil. You can use copy paper or line paper. Doesn't matter. Just blank, so that show all your work. If it's easy for me to follow, easier to grade you and gives you full credit. Okay. Any other questions? Either the e-portfolio assignment or for Unit 4. Do we understand how to balance equations okay? We're good with that? What about types of chemical reactions? What are the 3 types? Uh-oh. Yeah, what are the 3 types of chemical reactions? Did I say equations? 3 types of chemical reactions, my bad. Gonna have to get these down. Do you want to write them down? We're good? Okay. So we got precipitation, reaction. And do we know how to classify if a chemical reaction is precipitation?
The residue is left.
What?
The residue is left on the bottom.
The what is left? What?
The residue, the precipitation.
Okay, yeah, if it forms a precipitate, how do we know that? How do we know if a precipitate is formed?
A down arrow in the equation.
A down arrow?
Yeah. After the compound is left.
So let's see. What about this one right here? Potassium nitrate plus sodium carbonate. Let's say that's aqueous, and that's aqueous. Is that a precipitation reaction?
Potassium carbonate is down. And sodium nitrate.
What do you mean is down?
It will left in the reaction.
It reacts? Is that what you said?
Yeah, it makes potassium carbonate and sodium nitrate.
Potassium carbonate and sodium nitrate. So is this a precipitation reaction? Why not?
Because they're both soluble. Well, potassium and sodium are both soluble.
Yeah, they're both soluble. No solid is formed. So what do we call this kind of reaction? Why?
Because it's all still just.
Yeah, they're all dissociated in aqueous solution, and nothing happens. They just dissolve and stay dissolved. And dissolving is not a chemical reaction. That's a physical change, right? So this is no reaction. But if we have something like potassium nitrate, that's not a good one to do. Potassium hydroxide, and let's say silver. No, let's do iron chloride or something. Okay. Is that one a precipitation reaction? So these guys swap places, right? We got potassium chloride and iron hydroxide. Iron 2 hydroxide. Which one is a solid? Is that one a solid? Look at your chart. That one, it has potassium, so it's aqueous, right? This one right here is not on the list. It's not on our chart, so that one's solid. That one makes it a precipitation reaction, right? We're good? So if there's a solid coming from two aqueous solutions, we have a precipitation reaction. But if maybe it doesn't say this part, you will have to look at your chart that I gave you, right? Say, okay, is this going to form a solid or not? If it's soluble, it's going to be aqueous. If it's insoluble, if it's not on the chart, then it's a solid. And there are some exceptions on there, so we have to check, right? Okay, what's another type of reaction besides precipitation reaction? Acid-base reaction. Do we know how to tell if it's an acid-base reaction? What tells us it's an acid base? What tells us it's an acid, guys? If hydrogen is the cation, right? Yeah, cation, cation, same thing, right? Okay, if hydrogen is the cation, so it's H, we could have anything. HCl, HBr, H2SO4, all those, right? There's an acid. But if we don't have a base, it makes it not an acid-base reaction. We have to have both an acid and a base. How do we know it's a base?
It's a hydroxide.
If it has hydroxide in it. Something like sodium hydroxide, right? And what does an acid-base reaction do? Also called a neutralization reaction. It makes water and salt. Doesn't have to be the kind that we eat. There's a lot of different types of salt. Another ionic compound, right? So that means this is going to be aqueous. Do we know how to do a net ionic equation? On either one of these, we look at our products, right? Our products is either the solid or the liquid. It's not aqueous. That's not a product. That's dissolved, right? And then our reactants are going to be whatever makes that, right? The ions that make up that. So this is H plus from here, plus OH minus from here, making H2O as a liquid. Good? Questions? If you don't get it, I would ask this question. Can we do another one, please? But you know if you get it, you know if you don't. Not a bad thing if you don't get it yet, but let's just make sure we got it. And what's the third type of chemical reaction? Redox reaction or oxidation reduction reaction. Call it either way. Good. And how do we tell if it's an oxidation reduction reaction or a redox reaction? Yeah. If it's not, but how do you tell easily if it's not one of the other two? You're right.
If you don't start with the aqueous.
Okay. If there's no aqueous, even more than that. Gaining electrons or losing electrons. Yeah, and it's harder. That's a hard way to tell. And I kind of showed you how to do that, but I'm not going to really. I think what you mainly need to know is which one is the oxidation, which one's the reduction, right? Reduction lowers in charge. That means it gains electrons, right? Oxidation increases in charge. That means it loses electrons. If it forms carbon dioxide and water, that is a type of oxidation reduction reaction. But there's more of them than that. But yeah, you're right. That's one we did. Easy way to tell if it's an oxidation reduction reaction, if it's not a double replacement reaction. That's it. And when you said if it's not precipitation or not acid base, you're right. But what about this? Is this one right here a redox reaction? It's not a precipitation. It's not an acid base. So should we just call it an oxidation reduction? We should not, because this is no reaction. This is a double replacement. I mean, it's really not, it's not even a reaction at all, right? But, so you gotta check, so if it's a double replacement reaction, it's either precipitation or acid base. If it's not a double replacement reaction, it is an oxidation reduction reaction. That's the simplest way to tell. Now, there are cases, kind of like the no reaction one. There are cases where it's not a double replacement reaction, it's not an oxidation reduction reaction either. But we're not going to go there. We're going to keep it simple here. And so besides this, you also need to know which is oxidized, and which is reduced. Should we do an example of this? Okay. Let's say we have aluminum plus HCl gives us AlCl3 plus HCl. Is this a double replacement reaction? Kind of looks like they swap places, right? But this one doesn't take anybody, right? So this one's all by itself. This one was all by itself, now this is all by itself. We call this a single replacement reaction. Okay, this one only has one, so that's not a double replacement reaction. You have to have two compounds for double. Okay, so is this an oxidation reduction reaction? Most likely yes, right? Now how do you tell? How do you tell which one is reduced and which one is oxidized? What's the charge of this guy right here? It is if it's an ion. Is it an ion all by itself? It's not. All by itself, it's neutral, right? This is also all by itself. That's neutral, that's zero, right? This one right here, what's the charge of that guy? +1. What's the charge of that guy? -1. What's the charge of that guy? +3. What's the charge of that guy? Okay. Is this one oxidation or reduction? Does it gain or lose electrons? No, it stays the same. So that one's not either. What happens to aluminum? It goes from 0 to +3. Does it lower in charge or raise in charge? It lowers in charge. That means it's reduced. Or in other words, it gained electrons, right? Went from 0 electrons to, no, it lost electrons. Sorry, did I say gain electrons? My bad. It lost electrons. Lost electrons, but it gained in charge. So, did I say that one was reduced? Holy goodness gracious. You guys are probably thinking, what is wrong with this guy? Yeah, sorry. I flubbed it. All right. So, yeah, we go from 0 to +3. We go up. It's not reduction, right? And this one right here goes from -1 to 0. It is reduced. Sorry about that. This is oxidized. Are we good? Okay. Oxidized means what? What's happening with the electrons? We're losing electrons. And this one is gaining electrons. So that's all you need to know. Wonder if I had to show you one without ionic compounds. Just, I don't think, we'll do it just to be on the safe side. Okay? Okay, so let's do the one we did in class not last time, the time before. So we got C3H8O plus oxygen gives us carbon dioxide and water. Is this a double replacement reaction? No, it's not. That means it most likely oxidation reduction, right? Okay, so we can do, this is still an atom all by itself. That's a zero charge, right? But none of these are ionic compounds. Maybe I shouldn't. No, I'm not going to do this. Because that's a lot more information you have to know, and we're not even getting that far. We'll just keep it simple, guys. Keep it simple. But you can do ones with ionic compounds, right? Okay? We'll just keep it simple. Okay, those are the 3 types of reactions. Do we have any questions on different chemical formulas? Empirical formula, molecular formula, percent composition? Okay, what else? Yeah, Parker.
On one of the pre-readings, we had to identify like a strong, weak base, acid base. Do we have to do that? No, we'll do that on the test.
No. But here's how you tell if it's a strong acid. If it's a binary acid, HCl, HBr, HI, right? Those are strong. H2SO4, that's strong. And HNO3, that's strong. And the thing that makes these strong, these guys right here, is nitrate. Nitrate is always soluble. And what makes it a strong acid is it dissociates completely, right? We said an acid and a base has to be aqueous, right? If it's a strong acid or a strong base, either one, it has to dissociate completely. That's what makes it a strong acid or a strong base. Okay? Sulfate is also one that dissociates, right? It's soluble. It has exceptions, but for the most part, it's soluble. What about this one, H3PO4? That one's not a strong acid because this one doesn't dissociate completely. How do we know? Because it's not on that list. It's not on that chart, right? So those are our strong acids. Strong bases, anything with hydroxide in it. Done. But that's all we're dealing with in this class. Because if you have a strong acid mixed with a strong base, you'll get a neutralization reaction. And it'll form salt and water. That's all we're dealing with in this class. So I don't think you have to know that. I don't think so. I think critical chemistry. Was it? No, that was the reading. Pre-reading?
Yeah, on the pre-reading test.
Yeah. And the practice tests are even harder than the real tests, so yeah, I think that's it. Anything else? Anything you're afraid of? You don't feel like you got it down? Okay, you guys having your updating your reference sheet for the final? Because remember, on the final, all you get is one page, double-sided. And of course, I'll give you the periodic table and that other reference sheet, right, with the electronegativity chart. Yeah, make sure you have that complete for ready for next Thursday, week from today. All right. We pretty much covered everything for Unit 4, unless you guys have questions. Well, that's all I have for you. If you guys don't have any questions, I don't want to keep you here. But if you do have questions, I'll stay as long as you need. If you want to spend some time working on the portfolio assignment, I can hang around for a minute. Or for more than a minute. For almost an hour, right? Whatever you guys want or need. But if you're good, I don't want to hold you back. You can take off or whatever. Okay, the solubility chart. So we have soluble ions. And over here we have exceptions. Okay. Alkali metals. Or we can say group 1 elements. Ions, actually. So this is like lithium, sodium, potassium, and so on, right? And what these guys are soluble. What's the exception? There is none, right? No exception. Then some polyatomic ions, such as nitrate, ammonium, perchlorate, acetate, and these guys are soluble with no exceptions. And then
There's all polyatomic ions or just these four?
just those ones. Yep. Well, there's one more, but it has exceptions. So halogens, such as chlorides, bromides, and iodides, not fluorides. And these guys are soluble unless it's bonded to lead 2+, silver 1+, and mercury 2+. And the last one are sulfates, SO4 2-. These guys are soluble except with lead 2+, mercury 2+, barium, and strontium ions. And that's it. If it's not on that list, it's insoluble, right? If it is on this list, it's soluble, except if it's with these exceptions, then it's insoluble, right? Good? Anything else? Yeah, make sure you have this down or on your reference sheet.